lesson is going to start Unit 6. We're going to talk today about sinusoidal graphs. As part of your notes, you'll notice that there is a GeoGebra link at the top. I encourage you to explore that GeoGebra link as it has lots of flexibility that shows sine and cosine as graphs, specifically with how it is able to maneuver from the unit circle to the two-dimensional x and y graph and see how they come together. Once you do that, then come back to our lesson here and we'll talk a little bit about how we can graph these and some of their properties. So a periodic function is a function for which a specific horizontal shift, we'll call the shift P, results in the original function for all the values of x. When this occurs, we call that smallest such horizontal shift with P greater than 0, the period of the function. Below I've got the graphs of sine and cosine. Let's talk a little bit about the domain, the range, and the period of each one. The domain of the sine function, if we notice the left and the right hand side, will continue forever and ever in both directions. So the domain is all real numbers or negative infinity to positive infinity. The range is a little different. The range, its highest value is 1 and its lowest value is negative 1. So our range is restricted to negative 1 to positive 1 included. And the period for which our graph starts and then begins to repeat itself is 2 pi. I've got another picture just below that's also sine. If I were to continue our top graph and continue moving it to the left-hand side, we see that the graph is symmetric about the origin. So we see it's symmetric about the origin, and therefore the sine function is an odd function, since it reflects across the origin. Looking at cosine, cosine we see is just shifted where the highest point lands at 0, 1 instead of the highest point landing at pi over 2, 1. Pi over 2, 1 is where the highest point lands for sine, whereas the highest point for cosine is 0, 1. So it's shifted to the left just a little bit. Its domain is also negative infinity to positive infinity with a range that is also negative 1 to 1 included, and its period is also 2 pi from the time it starts until the time it begins to repeat the pattern. We notice though that when I expand into the negative values with cosine, that we are symmetric about the y-axis. So the cosine function is an even function. Both of these are called sinusoidal graphs because the shape of the graph begins repeating after 2 pi. Let's head to slide 2. We just identified that the sine is an odd function, which is symmetric about the origin. So when I take sine of the opposite of theta, I end up with negative sine of theta. And since the cosine is an even function, which is symmetric about the y-axis, cosine of opposite theta is equal to cosine itself. These angle identities are on your identity sheet for your trig identity values. Let's simplify sine of negative theta over tangent of theta. Notice in the numerator we have a negative angle identity. So I'm going to rewrite it using the negative angle, pulling that negative out front, giving us negative sine of theta over tangent of theta, and then rewriting tangent as sine over cosine. So I'm still going to have negative sine of theta over sine of theta over cosine of theta. Rewriting this as multiplying by the reciprocal of cosine of theta over sine of theta. Our sine of theta, since we are multiplying, have a common factor. We can eliminate them. So therefore we have negative cosine of theta as the ending identity result. Let's move to our next slide, where I have a couple of different examples. It's telling us that a point is rotating around a circle of radius 3. Sketch a graph of the y-coordinate of the point. I've graphed it here on the right-hand side, but how do I get this equation so that I know that it's what it's going to look like? It's asking for the y-coordinate of the point. We know how to find the y-coordinate because y is equal to the radius times sine of theta. We know our radius is 3, so y is equal to 3 times sine of theta. Our amplitude is oscillating. If we look at the picture, notice that between the highest and the lowest point is 3 units. Between -3 and +3. This wave amplitude is 3. So the amplitude is from the middle of the graph to the highest point, and from the middle to the lowest point is 3 units. So we can say that the amplitude, we're going to talk more about this here in a little bit, the amplitude is 3. It's not going to be 6, it's the distance, it's the halfway distance between the highest and the lowest point. What is the amplitude of the function 7 times cosine of theta? So I put into decimals y is equal to 7 times cosine of x, since decimals likes the x value. I see our highest point is 7 and our lowest point is -7. So halfway in between is 7 units. The amplitude is 7. It is directly related to the value in front of sine or cosine. The amplitude is directly related to those values that we see, which is very useful. Let's go to the next slide. A circle has a radius of 3 feet, and it's mounted with its center 4 feet off the ground. The point closest to the ground is labeled P. Sketch a graph of the height above the ground of the point P as the circle is rotated. Then find a function that gives the height in terms of the angle of rotation. How do I get then from the picture of what we're identifying with the circle that is going around to the graphs below? Let's talk a little bit about this. I know that from the ground to the highest point is going to be 7 feet. We'll put it over here. I know that from the ground to this particular point is 1 foot. So 4 feet plus the 3 feet radius is giving us that 7 feet. So when I'm looking at the graph itself, I'm going to take a quick look at the blue graph down below. I see that the point at which my graph is starting is at 0, 1. So this is going to be point P. If I were to graph this, I know my highest point is going to be 7 feet. I know that it's going to be 7 feet once I rotate 3 feet around. So I know this point has to be about 3.7 up here at the top of this blue one. I also know that that pi is halfway around the circle. So when I'm thinking about pi, halfway around the circle is pi. So when I go from point P all the way around, halfway around the circle to my highest point, that is pi radians around the circle. So I know that my x value has to be pi, and my highest value has to be 7 associated with that. At which point, once we make our full circle all the way around to 2 pi units, we're back at 1 foot above the ground. When I'm looking at the center of my graph, like the center of the blue line about here, I know that my amplitude has to be 3, it's 3 units from here to here. I can count 1, 2, 3 units. So I know my amplitude is 3. I also know that my graph is shifted up 4 units, because notice here that the center of my graph is not at the origin, but rather shifted up 4 units. So center is shifted up 4 units. Cosine would be the best to describe this, where my cosine graph is flipped over. Instead of the normal cosine graph being my red one, what makes the most sense is if I reflect it. So my graph for this equation, we'll call it h of theta, is going to be the amplitude that is reflected cosine of theta plus 4. So this negative reflects across the x-axis. So it's reflecting up and down. The plus 4 is the part that is shifting my graph up 4 units. So when we talked in college algebra about transformations of graphs, those pieces are still following us as we're talking about sine and cosine, identifying which graph would be the most applicable based on what we're looking at. So it's helpful to look at cosine itself or sine itself and compare it to a reflected version, because sometimes one is better than the other. This also leads us to more information about how we write equations. What we found by the shifting up or the shifting down is what we call the midline of the function. That plus 4 is the midline of the function. The center value of a sinusoidal function, the value that the function oscillates above and oscillates below, is called the midline of the function, and it directly correlates to the vertical shift. Notice we have it represented by a plus k. It could be a negative too if we're going down units as well. Noticing here at this next graph, we've got f of theta is equal to 3 times cosine of theta minus 4. Sketch the graph of this function. I know that my function is going to oscillate between 3 above and 3 below, the midline, and my midline is found at negative 4. So if I were to look at negative 4, y equals negative 4 here, I know that my value has to oscillate 3 above this line and 3 below this line. Knowing that it is cosine, I'm going to have my my y-intercept just shift down 4 units. So instead of being at above the x-axis, we're going to end up moving below the x-axis. So y is equal to negative 4 is the midline. And definitely use decimals to help us graph these to verify them, especially if you're new to utilizing sine and cosine. Definitely rely on decimals to help graph until you're starting to see similarities with what we're talking about and the equation itself. Let's look at example 6. It says that a point completes 1 revolution every 2 minutes around a circle of radius 5. Find the x-coordinate of the point as a function of time if it starts at 5, 0. So we have 1 revolution every 2 minutes. 1 revolution every 2 minutes is our angular velocity from our last unit. We know that it rotates 1 revolution, or 2 pi, every 2 minutes. Using ratios, that would mean it would rotate pi every 1 minute. Therefore, theta of time is equal to pi times how many, the time, radians. We also know that x, because they're asking for the x-coordinate, is equal to the radius times cosine of theta. This would provide us with x of theta is equal to 5 times cosine of theta. What I'm able to do now is replace pi t radians where our theta is, since we know what theta is at. Oops. So 5 times cosine of pi times t. In this instance, I used pi x in decimals so that it would graph appropriately. Notice what's happening. I graphed in purple just 5 times cosine of theta, so 5 above and below the midline. But notice what's happening once we insert a pi value inside that transformation, inside that parenthesis. It's giving us a squish, a horizontal compression. So it's messing with the period of the cosine function itself. It's squishing it down. It's directly correlated to putting something inside that parenthesis there. Let's take a closer look on the next slide. So that last example, we were able to see a horizontal compression. So horizontally compressing it down, which changed the period of the function itself. We can relate a stretch or compression by giving b of t on the inside of the sine or cosine function. We know that the period is the time it takes for sine or cosine to complete a revolution of circle. Right now, currently, it takes 2 pi over a certain amount of minutes to do that. We can identify the b value by taking 2 pi over our p value, the p value being how fast it can do that, or solve for p by having 2 pi over our b value. So we've covered a few transformations so far, and I have them in purple below. We've covered the amplitude. The amplitude is the above and below the midline, how far up and how far down that will go. So almost that vertical stretch. How high and how low are we going to go from the midline? We've talked about B. B is the compression inside that value. That period can be found by taking 2 pi over B, or we can solve for B and take 2 pi over the period. K is known as the vertical shift, and it tells us the midline, where the midline of our function is. heading to the next slide, let's go a little bit deeper into the inside of the b value and dive a little deeper into that. What is the period of the function? We have f of t is equal to sine of pi over 6t. Well, right now we have been given the b value and we're looking for the period value. So we can find the period by taking 2 pi divided by our b value, or 2 pi divided by pi over 6. We know we can multiply by the reciprocal, which gives us 12. So the period is 12 units. Below, I have the picture of regular sine function in red, and I have sine of pi over 6x, where I can see that the period is certainly stretched out, where sine here starts and ends here. There's one period. Notice that it takes this black line a lot longer, 12 units, in order to complete one rotation. Let's see that in action again with example 8. A bicycle wheel with radius 14 inches as the bottommost point on the wheel marked in red. The wheel begins to roll down the street. Write a formula for the height above ground of the red point after the bicycle has traveled a certain amount of inches. Notice that our lowest point, it tells us it's starting on the ground. So it starts at 0 rather than at a high point. Our highest point, if it's 14 inches here, our highest point up here is going to be 28. So it's going to oscillate above and below 14. So we know a couple of things. We are going to use a cosine of b of t plus k is the value we're going to use. I'm also, knowing that we're starting at the lowest point versus cosine, which starts at the highest point, but it does have the qualities of cosine just looking at its shape. So instead of having a positive, we are going to do the opposite so that it reflects from the highest, so that it starts at that lowest point instead. And it's pretty frequent that that happens. So we know our A value is going to be 14. But opposite of 14, because it's oscillating above and below by 14 units, but we're doing the opposite because we want to reflect from the original. Cosine of theta, and the midline is at 14 as well. So a unique case where that happens. The period may be affected by our arc length along the circle. So let's stop and think about what that might look like. So the arc length is equal to the radius times theta, and x is equal then to 14 times theta. So theta is equal to x over 14. So our period is affected a tish bit. So this part, now that we know what theta needs to be, we can substitute it back into our equation so that the height with respect to x inches is equal to negative 14 cosine times of x over 14 plus 14. Let's talk a little bit more about the period. We know that the period is equal to 2 pi over b. We found b to be 1/14. So 2 pi times 14 over 1 is equal to 28 pi. This shouldn't surprise us because it is the circumference of the circle itself. So it is the circumference of the circle itself. So it shouldn't surprise us that the period, how long it takes to go from start to finish, would be the entire circumference of the circle. Let's wrap it up with one more example here. Determine the midline, the amplitude, and the period of the function. So it's already written in standard form. We know that first value is our A value, so the amplitude is 3. We know our B value, which can help us find the period. We can find the period of this particular sine function by saying P is equal to 2 pi over B, or 2 pi over 2, so the period is pi. And we know our K value, which is the midline. So the midline is y equals 1. I've got them graphed here below, which can be very useful for us to see. We see the midline here in blue. The graph is shifted up. This is sine. Typically sine starts down at the origin. So it is shifted up 1 unit, which is at the midline. It is 3 units above and 3 units below the midline. The period typically would need to be 2 pi, but we notice that from the moment it starts to the moment it starts again only takes pi units, or about 3.14, etc. So pretty interesting to see how they correlate together when we see it on the graph itself. So please, please, please utilize Desmos to help you visually see what these sines and cosine graphs are doing.